Welcome to the 24th session on operating system and Linux. I'm Manibhushan D'Souza, and in today's class, we are going to look at deadlock detection. So we are going to look at the methods that are used to detect the deadlock. Now let's look at the problem of deadlock. And we know that in the previous classes, we know that either when the deadlock occurs, before the deadlock can occur, we can prevent it, or you can give the resources in such a way as to avoid the deadlock. These two things you have seen in the previous classes. But suppose if you don't take any actions, what do I mean by saying that is, if you don't prevent the deadlock or if you don't avoid the deadlock, then definitely there may be a situation wherein the system may end up in a deadlock because you don't prevent it nor you avoid it. So there is a chance that the system may end up in a deadlock. And we know very well that when the deadlock occurs, the throughput of the system drastically reduces because no process is able to continue. So we have to, if you don't take any prevention, nor if you don't avoid it, then we have to go for the next option, that is the detection. So because we are not preventing the deadlock, nor we are avoiding the deadlock, then we must provide a technique or algorithm that will examine the current state of the system to detect whether there is a deadlock or not. So that's the other possibility. So either you take the precaution or you don't take the precaution and then go and check, go to the hospital and then make a test and then find out whether you have the disease or not. So that's the thing. Okay, so either you don't go in a place where there is a disease or where you may get the, it's like if you go in cold, you get you may catch no, if you go in a wet place, you may catch cold. So either you don't go there or avoid when you're traveling, avoid those routes. If you don't do it, then you go and verify whether you have flu or not. Okay, so this is the same idea. We are avoiding, not we are avoiding, nor we are preventing. In that case, there may be a deadlock. So go and check whether there is a deadlock. If there is a deadlock, recover from the deadlock. So this is what we are going to see now. We will not see how to recover from the deadlock, that is out of scope for your subject, but we will just see how to detect the deadlock. Okay, so the detection and recovery requires some overhead because we have to go through the system to find out whether there is a deadlock or not. This is an extra effort that we have to do it. So this requires some information to be maintained about whether the system is in deadlock or not. So it's like every now and then you go, because we are not taking any precaution, every now and then you just go and verify whether any system is in deadlock or not. If not, well and good. Otherwise, again go and check whether all of the system, all the processor, whether they are running or is there a deadlock. So this extra effort is required, and some information need to be saved to find out whether there is a deadlock or not. Okay. Apart from that, if there is a deadlock, you know very well how to avoid or how to recover from the deadlock. Is one of the scenario is you find a victim and then just stop that particular process and take back all the resources that are given to that, then continue. So there is a deadlock, there is insufficient resources are there, everybody is waiting for the resource, nobody can continue. In that case, what you do is you find a victim process, just close it down. It's like kill that process and recover all the resources that are given to it, and then see whether you can continue with it. So this again is some extra effort that you need to do. So there will be some potential losses because the process might have done 90% of its work might have been done and it is the victim. Then you will to cut that process, then the process has to rerun again. So again that will be an extra effort. Okay, it's like you go and find a process, victim process, kill it and take back its resource. But what if that process has done 99% of its work, only 1% is remaining? If you kill it, it will have to redo that entire 99% again once it is restarted. Later, definitely later you are going to start it. So when it is restarted, it has to redo it again. So this is again an extra effort. Okay. So now let's look at how we can check whether there is how we can detect whether there is a deadlock or not. There are two ways in which you can do it. One is when there is only one single instance of the resource, and when there are multiple instances of the resource. What do I mean by saying single instance of the resource? Suppose if your computer has only one printer, that is one resource, one hard disk, one resource, one monitor. So all the resource, whatever resource you can think of, there is only one instance of it. In that case, we can use one algorithm. Suppose if the computer has two printer, four hard disk, that is multiple instance of the resources. So there will be multiple instance of the resources. In that case, we can have some other type of algorithm. Now let's look at the first one, that is if there is a single instance of each resource type, then what you can do? Then we can detect whether there is a deadlock or not by using our resource allocation graph. We will not use the same resource allocation graph, but we will slightly modify that graph and then use that graph to detect whether there is a cycle or not. And this modified graph, which is taken from the resource allocation graph, and you make some changes to it, and that one is called as wait for graph. So this, what is this? A wait for graph is a variant, a small variation of the resource allocation graph. So how do we achieve that thing? Now in the resource allocation graph, we have like this. So we have some process, okay, some process P, let's say P1, and it is making a request to a resource, say R1. You recall that this is your resource graph. Suppose if you have one other arrow here and one other process on the other side, and suppose if you say this is P2, what is the meaning of this? So what is the meaning of that? So it means process P1 is making a request for a resource R1, which is already allotted to the resource to the process P2. So the process 1 is making a request, give me that resource, but that resource has already been given to somebody else. So what the process P1 has to do? It has to wait. So process P1 is waiting for the resource R1, but the R1 is there with someone else. Okay, so in our case, in case of this is your resource allocation graph. When it comes to the wait for graph, there is a small variation, and the variation is when you have this situation, this particular part is pulled out. So in case of a resource allocation graph, what is being done here is, so let me redraw the thing again. So we had a process which is called P1. It was waiting for the resource that was used by other process called P2. So this is how it was there. In between, that resource was there. When we draw this wait for graph, what we do is we will not consider the resource. Instead, we just draw an arrow like this from P1 to P2. So if there is this is not the resource allocation graph, I am talking about the wait for graph. So in the wait for graph, if you have an edge from P1 to P2, what is the meaning of this? Meaning of this is the process P1 is waiting for a resource, okay, let's say any resource. It is waiting for the resource, let me say R, which is already been allotted to process P2. So this is as simple as that. So what is being pulled out is this resource has been pulled out, a direct edge has been made. So this is what it says. So if there is an edge from Pi to Pj, what does the meaning of that? That means there is a process waiting for a resource R which is been given to some other process Pj. So simple as that. Now let's look at the resource allocation graph, which you are already familiar. So in the resource allocation graph, you will notice here, so a process P2 is waiting for the resource R4, and that resource R4 is already being used by P3. So if you remove this part, what you'll get direct here. Okay, so instead of drawing a curve like this, you can straight away say P2 is waiting for P3. So what is the meaning of that? P2 is waiting for a resource that is already given to P3. So P2 is waiting for a resource that is already given to P3. In the same way, P3 is waiting for a resource R5 which is already given to the process P4. How do you do that? You directly draw the graph. P3 is waiting for a resource that is already given to P4. What about P2? P2 is waiting for a resource that is already given to P4. How do you draw that? P2 is waiting for a resource P4 which resource which is already given to P4. The next one you have here is P4 is waiting for a resource which is being used by P1. How do you draw that thing? P4 is waiting for a resource which is already given to P1. Again, P1 is waiting for a resource which is already given to P2. How do you draw that? You're going to draw like this. So in this graph, this is called as wait for graph. So in the wait for graph, what is not there? The resources in between the resources not are being pulled out. Okay, the same way this is also true. So now you get this only the process. Now find out whether there is a cycle. You notice that there is a cycle here. Okay, there is no cycle here because it is not coming up. Okay, but definitely you may have one more cycle, a bigger cycle. Okay, like this. Now in any case, if there is a cycle, that means there is a deadlock. So it's simple as that. So you draw a wait for graph. Okay, and if there is a cycle in that graph, that means there exists a deadlock in the system. Okay, what has to be done? So how does the system works then? So this system has to regularly maintain the wait for graph to periodically check whether there is a deadlock or not. If there is a deadlock, it has to somehow do something to come out of the deadlock. So it's like every 10 minutes the system will go and check whether there is a deadlock by drawing the wait for graph, and if there is no deadlock, well, if there is a deadlock, it will do something to come out of that. Okay, what's the disadvantage of this one? Disadvantage is this can be used only in a situation wherein every resource has a single instance. That means there is only one printer, only one disk, only one. All the resources are only one instances are there. Then this is well and good. If there is more than one instances, this graph cannot work there. In that case, what to do? If there are several instances, then we will fly back to the same old Banker's algorithm. So I've already talked about this Banker's algorithm previously. So in this Banker's algorithm, we know how to allocate it. The same but slightly modified version. It is not the exact, we are not copy pasting the Banker's algorithm here, but a slightly variant of the Banker's algorithm is being used here. So when there are multiple instances, like if you have 2 printers, 5 disks, 10 monitors or something of that type, in that case you go for variant of Banker's algorithm. This particular algorithm, like the Banker's algorithm, this also makes use of different data structures. Now one of them is the available. So what is the available? Available will say how many resources are available at this instance of time. So out of 5 printers, how many printers are available now? How many of them are free? So you can say 2 are free. So you make a list like this. So out of 5 printers, how many are there? You may say that 2 printers are there. Out of 10 disks, how many disks are free? You may say that 6 disks are free, like that. So you create a vector of length m and you maintain them. Next one is the allocation. Allocation is which resource is given to which process. So you can say that for example you may have process 1, you may say, okay, then you have the printer, then you have the disk, hard disk, let's say hard disk, and let's say monitor. So process 1 is given to printer, 1 hard disk, 1 monitor. Process P2 is given 3 printers, 2 hard disk, 2 monitor, like that. So this is it's a matrix. You notice that that's what is that. How many are being allocated? The next one is the request. So you know very well, you give something and all the processes are very greedy. So process P1 may say that after some time the process 1 may say that I want some disk, some hard disk, some monitor. So after some time, this is not the allocation. This is it request. It comes back to you and again say, can you give me 1 printer? Can you give me 2 hard disk? Can you give me 1 more monitor? The process P2 may come and then it may say, can you give me 3 printers again? Can you give me 2 hard disk again? Can we give 2 monitors again? So this is again a matrix. You see that, and that matrix is a request matrix. Request matrix means it is making a request to this. So request of I comma j means so ith process is making a k number of a request. So k is 2 in this case, of a processor of type j. So that's simple as that. So it is, you know how to read the matrix. And now I'm going to first show you how that algorithm really works, and then I will come back and tell you how that the algorithm is written. Okay, so first look at the example and then let's look at how the things are going to work. So let's go here and let's see the current resources. There are 7 instances of A could be printer, A could be anything. There are 2 instances of B could be hard disk or anything. There are 6 instances of C. So 3 resources are there, A, B, C. First one has 7 printers are there, 2 hard disks are there, 6 monitors are there. You can take anything like that. Okay, so some resources are allocated. You know, whenever a process starts, you give some resources to it. So P0 is given 1 instance. So there are 2 instances are there, 1 instance of B. It is not given any other resources. P1 is given 2 instances. There are 7 were there, 2 instances of A, nothing of B or nothing of C. P2 is given 3 instances of the A. Remember, out of 7, 2 are already given, then 3 are given, so remaining again 2. And B, nothing has been given, and C, 3 instances are there. 6 were there, 3 are already given. For P3, the remaining 2 are given, remaining 1 is given, and 1 is given. For P4, again 0A, 0B, 2 C are been given. If you count all this, these are already allocated, already you have already given to them. If you count all of them, how many are there? So 2 plus 3 plus 2, 7. 7 were there, 7 are been allocated. So how many available to you? All are given, so 0 is available. 2 were there and 2 are given. How many is available? 0. You don't have anything. Let's look at C here. 6 were there. How many are allotted? 6 are allotted. What is available with you? Nothing is available. So you are empty now. You gave every resource. Now the question comes. P1 is not making any request. P1 is a very good process. It says, I don't want anything. I don't want a resource. I'm happy with the 1. P2 is not so happy. P2 says, give me 2 instances of A. Remember, you don't have anything here. You gave all the resources. But P1 is coming and asking, can you give me 2 instances of A and 2 instances of C? From where will you get it now? P2 will come and say, I don't want anything. I'm happy with what you have given. P3 will say that, no, can you give me one extra of A? You have already given 2, 1, 1 to me, but I want one extra A. P4 will come, can you give me 2 more? Already 2 I have given you, but I say already 2 more. So now what to do? Nothing is there with you. You are empty, nothing is there. How can you solve this problem? To solve this problem, the concept is very simple. Now first find out the people who are making zero request. Now what is the meaning of saying zero request? Now remember, if the P1 comes, you will tell the P1, wait, I don't have anything now. If P3 comes, you say, wait, I can't give you anything. I don't have anything with me. How can I give you? If P4 comes, you say, I don't have anything. Wait. But P0 is not going to come to you because it is not making any request. So what you will do, you will wait for P0 to complete. Let it complete. So if P0 completes it, remember you gave one instance of B, it will return back. Remember, if you give a hard disk to the process P, after completion, it will return the hard disk. It will say, okay, I have done input output operation. You give the input output operation to somebody else. So it's going to return the resources. See, when the process starts, you give the resource. Once it completes, it will return back the resource back to you. It's like you go to library, get the book, and once the due date is over, you will have to return. So once your turn is over, you will return back. So P1 is a very good one. It is not making any request. So you just wait for P1 to complete. If a P1 completes, what will happen? It will return one instance of B. So how much you are going to get here? One instance of B. You got it. At least you got one. Now you didn't had anything, you were empty. Now one you got. Now go to this next one, P1. You go to P1. Can you satisfy this P1? It's not possible. What is the reason? P1 is not making any request for B. Even though you have one instance of B, P1 says, I don't want B, I want two instances of A, I want two instances of C. But you don't have that, so forget, you can't satisfy P1. Now go to P2. Now P2 is a very good process, very idle one. It just says, I don't want anything. God has given me everything. So what to do? Wait for P2 to complete. If the P2 completes it, it's going to return 3 instances of this and 3 instances of C. Okay. So assume that P2 has completed. P1 has already completed. P2 has already completed. So what you are left with? 3 from the return 1. 1 was already there with you, and it's going to return 3. So you are so happy that you got it. Okay. Now go to the next step. Okay. So in the next step, what you are going to do? Check for P3. Remember, you can come from here and then do it. Okay. Or you can go from here also. So let's go from here only. I'll continue from here. So look at the P3. P3, what it is saying, I want only one instance of A. You already have 3 instances of A. So you okay, you give, I'm going to give you one. That's the last one I'm going to give you. Take it and complete it. So you give one to which one? P3, and make it complete. So P3 will complete it. Once you give one, it says, okay, I will go for the completion. I will complete it. So if it completes, what you are going to get? It's going to return this. 2, 1, 1 was already given. So 2 plus 3, it's going to be 5. So it's going to return 5. Remember, 2, 3 already you gave. Even though you gave 1, it will also come back to you. Okay, what you give, it will come back to you. So 5 are there. 1 already there. So this becomes 2. And one more, it's going to come. This becomes 4. Now go for the next one, P4. So in the P4, what you notice, P4 is making a request for this 2. So 2 you already have it, just give it to P4. So you just give it to P4. P4 will be very happy. Okay, take it. P4 completes it. What is going to give? It's going to return it back. So you get 6. This is 2. This is 5. Who is not? This is completed. P4 is completed. Who is not completed? You come to P1 and say how much you want. It says, okay, I want 2 and 2. Take everything and complete it. And then once it returns back, you will get your last number. Remember, last number must be same as what you got here. If you get something extra, that means you don't know how to calculate. Okay, as simple as that. So this is how the algorithm works. Now just give you one small hint. Suppose this one, so that means to say that everybody is satisfied. That means this, what does that mean? There is no deadlock. See, if you can able to satisfy everybody, that means there is no deadlock. Nothing is going to happen. Just imagine the same situation. You had the same situation, but suddenly P1, P2 becomes greedy. Okay, and P2 just says, "Can you give me one of C?" Just no, P2 just becomes greedy and say, "Can you give me one more C?" In that case, what's going to happen? In this case, look at what happens. The algorithm comes here. P1 is a very good process. It says, okay, P1, you complete it. So P1 completes it, you get 1 of B. Okay. This is not possible because I don't have it. This one, what is saying? It is not saying B. It is saying, can you give me C? I can't give you. Okay, this means this can't complete. It goes here. It says, can you give me A? I can't. It says again, can you? So what is the meaning of that? Once you allocate the first one, you get only one. That's all. Others cannot complete. So P0 may go for the completion. P1, P2, P3, 4 are in deadlock. They cannot complete their work because they don't have the enough resources. Hope you get what is the essence of that algorithm. So let's go and let's look at the algorithm now. I'm going to go with the algorithm. So what does the algorithm say? Initialize work equal to available. So what is you take a separate variable called as work that is equal to available. What is this available? So take instead of available, take this as work. So work means what is available with me, how many resources are available. In my example, you didn't have anything, you are proper, you didn't have anything, but if you have some resources, take that as the first step. Next thing that you are supposed to do is go and check every process and see whether you have allotted any resource to it. At least one resource has been allotted or not. If at least one resource has been allotted, then it is not yet complete because you gave one resource. Until it returns back the resource to you, that has not finished it. Remember, if the process finishes it, whatever resource you gave, it's going to return it back to you. So finish is false means it has not completed it, it has not finished it. If it has finished it, it's going to get back. So if I finish of I is false means the process is not completed. So if the allocation, let's look at here the example that I have here, so the previous example, you notice that you gave at least one resource, either B, C or anything. If you give at least one resource, that means this process, none of them are complete because one process, it is taking one instance of B, it's taking two instances of B, it has not returned it, it has taken it but not returned it. That means it is still active. Now if you magically if you get one processor which does not take any resource, I don't know how it is possible because CPU itself is one resource. If there may not be any process that says I don't want any resource, in that case there is no process at all. Okay, so initially, just to say that all the processors which are working, they are all having allocation. So let's go to the next part now. What is the next part? Okay, suppose if you find one, that's what I told you. If there is one, I don't know, magically you get one process which says I don't want any resource, but I am still working. If you find them, then well and good, you just make it that has finished already. There is no point in bothering about it. See, if you have given some resources, then you can take back and give it to some other process. Suppose if you are not given anything, whether it is running or dying, who cares, because it has not taken any resources and it's not going to return anything to you. See, what is your intention? Your intention is I have given some resources to one process. If the process completes it, I will take back that resource and give it to somebody else. So that's your idea. Now, if the process has not taken any resources, let it go anywhere it wants, because it's not going to return any resource to you. And if it's not going to return any resource, why should I bother about it? So that's simple as that. If there is no resource that is allocated to it, then you just say it has finished. Whether it is done or not, it is finished, because there is no need to bother about it. Let's go to the second step. Now find one of the process which has not yet finished, which has the request less than work. So what is that thing? I have already done that. So find somebody whose request can be satisfied. See, remember initially what did I do? So P1 completes it, you get one instance. P2 didn't make any request, so that is it. Then I went to which one? So when P2 completes it, you get remember when let me show it one more time. When P1 completes it, it's going to return one instance of B. Okay, and it's not making any request. When P2 completes it, it's going to return three instances of A, one instance of already there, and three instances of this. Okay, so if P2 completes, you are in this case. Now find someone from this list who has the request which is less than available. So you notice this one. This is having request less than available. Okay, so that's simple as that. Can I satisfy them? Yes, this has a request less than available. Okay, so find someone whose request is less than available. Remember, I have renamed this available as work. I told you I will take that as work. So you find someone whose request is less than work. If you can't find them, then you are in deadlock. That's simple as that. So this is what happened in the last case. What happened in the last case? Last case, A became greedy, P2 became greedy. So you completed P1 and you got one instance of this, but you could not complete P2 because P2 was greedy and it requested one more C. Now with this you can't complete this because it is a request and availability is not satisfying. This can be done, this can be done, this can be done. You are in the definitely deadlock. Okay, so simple as that. So if you go to the step 4 and if you are so eager to go to step 4, what does the step 4 says? If you find that there is a process, it has not yet completed, at least one process has not completed and you cannot allocate them, that means the system is in deadlock. Suppose if that is not the case, if you are able to allocate, if you are able to allocate the resource, then what you do? Allocate the resource, ask it to complete and take back all the things that you have given. So simple as that. So what did you do here? In this case, P1 got completed and you got one instance of B and you asked P2 to complete faithfully. So P2 completed and it gave you three instances of this. One was already there and one instance of C was already there. So you got three instances of A, one instance of B and three instances of C. Now you notice the P3. P3 is making only one request. So its request is less than available. So give the request, give whatever P3 is asking for, ask it to complete. Once it completes, take back all the resources that you have given. How many resources you gave? So you gave 2 resources. 3 plus 2 is going to be 5. So you got 5 things back. Then you got 1 plus 1, it is 2, and 1 plus 3, it is 4. So give it and then add whatever that was allocated. So add it back to the work. So remember, again I am marking it as work. To confuse you, I am marking it as work. Okay, so this is what you do. So in the step 2, allocate it, finish it and give it get back the allocation. Work is equal to work plus the previous one plus 1. Okay, so like 3 1 1 was there. Okay, if you are giving it 2 0 0, so what is the answer? So this originally 3 1 1 was there, you give 2, that means it's going to be 5 0, so 5 1 3, so it will be like you have finished that process. Remember, you wait for the process to finish, so you say finish is equal to true. That's it. Go to step 2. What is the meaning of going to step 2 again? So you know very well, once this is completed, what you do? So this is completed, this is completed, this is completed. It's not the end up. Find one more again, finish it. One more, finish it. If you can finish everything, well and good. If you can't finish it, there is a deadlock. That's simple. That's a simple essence of that algorithm. This algorithm, I don't know whether you have studied about the order of operation. It requires m into n square operations because you don't study those things in your BSc. But just somebody asked it, you just mentioned that its complexity is m into n square. Okay, you are not studying the complexity of the algorithm and so on. So big O notation, omega notation, this kind of notations you have not come across. but when you come across you will come to know, but that's why I'm not explaining that. Suppose some people are there, they will ask during the examination what is the order of that, so order is this one. Okay, I will not explain that because it has to be explained in the data structure classes, not in this class. Okay, so this is the algorithm, that's the essence of it. Now if you like the operating system very much, and if you want to learn more on the operating system, please refer the Galvin's book on operating system. Thank you for interest, and we will meet again in the next class.